Today I'm going to talk about first order methods and especially policy gradients based methods. So here the idea is that instead of just using zero order method or zero order information, let's estimate the gradient of j of rho of pi theta with respect to the policy parameter. And this basically allows us to use gradient based optimization methods. So essentially we can do gradient ascents in order to maximize the performance. And these can potentially be more efficient in finding an optimum of the performance compared to the zero order methods because they benefit from more information, or they use more information about the problem. But then the issue is that it is not obvious how we can compute the gradients because, well, the performance j of rho of pi theta depends on value function, right? But value function is not a very simple function of policy because it depends on it depends on distribution of reward and transition dynamics and also the policy. So when we change a policy, essentially agent may go to different regions of the state space, collect different types of rewards. Now we want to not only, so it's a kind of non-trivial relation between the parameter of policy and this value function. And now what we want to do is that to compute the gradient itself. So see, if I change the theta a little bit, how much the performance would change. So this doesn't seem to be an easy problem. So one approach that however we can use is to use finite difference approximation of a policy gradient. So the finite difference is essentially a method, a numerical method to approximate a derivative using just numerical computation. And then the benefit of it is that we can compute the finite difference approximation of derivative just using zero order information. So the value of the objective itself. So just as a quick reminder, if you have a one-dimensional function f from R to R, the finite difference approximation of the derivative f prime, I show by f prime, is this essentially. So f prime of finite difference, so it would be f of x plus delta x minus f of x divided by delta x. So this is essentially the definition of derivative. We take delta x goes to 0. So, and usually we take a small step size essentially, or for delta x. So this is called the forward difference approximation because we start from x and we move forward a little bit and then compute the difference. So if this is kind of the function, so it's x, this would be x plus delta x. We approximate it with this slope essentially. So that's the idea. And then we can show that by Taylor's theorem, we can show that the error is not large. So assume that the function is enough differentiable. So what we have is that f of x plus delta x is f of x plus f prime of x times delta x plus the second derivative of x, f, at some point between x to x plus delta x. So this is z here, times delta x squared divided by 2. So that would be exact. So there exists a z between these 2 points where this is an exact calculation. So this is this mean value theorem. So the result would be that f prime of x would be this first term, which is essentially our finite difference approximation, minus f, the second derivative of f at some point here, plus a term that depends on delta x squared. So essentially, if everything is kind of continuous enough, it doesn't blow up. So this would be a finite number. So we would have an error of delta x squared. So this provides an approximation. Okay, we have a more accurate estimation, which is called central difference approximation, which instead of which computes f of x plus delta x minus f of x minus delta x. So we move forward and we move backward and then compute the difference and divide by 2 times delta x. And you can show similarly that this is a cubic error in the size of that delta x. So this is the idea is that we do this computation in order to approximate the policy, the gradient of policy or gradient of performance with respect to parameters of the policy. So what we can do is, if say theta is p-dimensional vector, so for each dimension, we do this finite difference approximation. So for the first derivative of j of rho pi theta with respect to theta 1 would be approximated by this j of rho of pi plus epsilon e1. E1 is a vector, so E1 is essentially that has the first element equal to 1, the rest would be 0. So essentially I move theta, the first dimension of theta epsilon forward, and then epsilon backward, compute the performance, and divide by 2 epsilon, and I do it for each of these p dimensions. So in total, I need to 2p times evaluation of j of rho in order to compute this. Okay, do you have any question? Okay, so there is a question in chat. So the question is that will evolution algorithms suffer from the problem of getting stuck at a local maximum a lot? So that's a big business. So one of the selling points of these evolution algorithms is that it can escape from local minimum. But in practice, it may get stuck. So in general, if you have a nonlinear function, which is not convex or not concave, finding global optimum might be very difficult. These methods, like evolution algorithms in general, they have mechanisms to escape from local minimum or maximums. Do they always work? Not necessarily, but usually they work better, I would say, in escaping local minimum than something like a gradient-based method, which definitely gets stuck in a local optimum. But I guess one comment is that these methods are very heuristic based. So there are a lot of heuristics using there. So, and people try it empirically. They don't necessarily prove things, not because they don't want to, but because it's very complicated. Except that for some cases, so for example, for some simple cases like evolutionary algorithm, evolution strategy 1+1, I guess there are some theoretical results that showing for these type of functions we can find the global minimum, for example. Yeah. Okay. Any other question? Okay. So this is finite difference calculation. So one question is that, two questions from you. If we have this policy gradient approximate using finite difference, how should we find the policy, the good optimal policy or a good policy within that policy space?
So do gradient ascent?
Right, yes, so we should now do gradient ascent based on this gradient information. But there is one challenge here. Can we compute these terms exactly? We cannot, because this is essentially the expectation of the value function, but we don't have the value function. So we are in the RL setting. So we have to interact with the environment by, say, using Monte Carlo estimate in order to have j hat n estimate of each of these parameters. And usually we have some kind of form of guarantee like this, that if you have n rollouts, we get an estimate which is order of 1 over square root of n accurate or close to the true value. Okay, so we cannot directly compute j rho of pi theta, but we can only compute j hat of n using rollouts. So we can replace j rho with previous page. Maybe this should be above here. With the corresponding j hats. And then this requires in total 2 times p times n rollouts. So because we have p dimensions for each of them, we have 2 j computation required. And then if we do n rollouts for each of them, so we have 2 times p times n. And then as you mentioned, if we have these approximated gradients, which has errors, 2 sources of errors, one is because of finite difference approximation, and the other is using j hats n instead of j rho, then we can do gradients ascents in order to move towards higher value of j of rho of pi theta. So basically we compute theta of k plus 1 would become theta k plus some learning rate times the gradient. So we move upward here. Okay, so this is a kind of warm-up approach. So this is feasible, but we can compute the gradient more elegantly. We don't need to use something like finite difference methods in order to compute the gradients. Okay.
So, Professor, I guess this type of thing would be best for like a model-free approach. I mean, like one where it's not necessarily an MTP. Would that be? Is that similar to sort of like that Monte Carlo thing that we did a couple like?
Right. If you mean this finite difference one or policy gradient in general?
No, the finite difference approximation specifically, because you're doing all the Monte Carlo rollouts and.
Yes, like for this, it is enough to be able to do Monte Carlo rollouts. So we don't benefit anything from structure of the MDP.
Of MDP. Okay.
So you can, some of the methods benefit a little bit more from structure of the MDP, as you will see later. So those may not, if those structure is violated, is not existing the problem, they may not be useful. But you still see that we can still compute something like policy gradient. I mean, maybe I guess I don't explicitly show it here, but you can do policy gradient a little bit more elegantly than this approach, even though the problem is not MDP, but is partial observable MDP, which okay. Okay, so that's, so now let's compute the policy gradient for the immediate reward problem. So this is simple. Basically, we don't have dynamics, we only have reward, and we are interacting with the environment, as you remember many lectures ago, and I'm going to review it. So this basically gives us some idea about what are the challenges and what are the general ways to compute this policy gradient. And then when we move to the policy gradient for continuing problem, then we only need, say, one more trick, essentially, to be able to compute it. Okay, so this is for immediate reward problem. We have a pi theta, which is stochastic and p-dimensional, and we want to maximize the performance for the immediate reward problem. So the interaction protocol was like this, that episode t, we choose xt from some distribution rho, and this is independent from previous iterations. So we randomly choose one initial state. Agent choose action at according to pi theta of xt. So agent sees what state it is, selects some action from its policy, and then the agent receives a reward RT, which depends on XT and AT. So it's a random variable that only depends on state and action. And then the agent restarts the new episode and starts an episode T+1. And this would be ranked independent from the previous episode, so, or the current episode. So for example, the reward that I get here doesn't affect where I will be, or the choice of action doesn't affect where I will be next. So this is an RL agent, RL setting, because rho and R are not directly available to the agents, but only through samples. So what I'm trying to do is that compute the policy gradients, but just using this sample information, this type of samples. And I do it gradually in several steps. Okay, so the performance measure. So is the setup clear? Okay, good. Okay, so the performance measure was, what was it? It was J of rho of pi theta, which is the average of value functions of following policy pi theta at when the initial state is distributed according to rho. So that was the performance. Here the value function would be essentially the reward. So it would be R of pi theta of x, because we only go one step ahead. So the value function would be the same as the immediate reward. So this is kind of like the simplifying step here that we are benefiting, but gradually we relax it in the next section. So let's write R of pi theta in a more explicit way as a function of policy. So it would be R of x and a times pi of theta a conditional x, d of rho of x and d of a. So we have integration with respect to action space weighted by probability pi theta of a conditional x, and then we are computing the expectation of R of x and a, and then we have another integration which is over states, which is according to this rho of x. So this is, we consider the action space to be continuous, and we assume that this pi of theta provides a density over the state space. So that's why I wrote it as an integral. If we had a discrete action space, it would be very similar. Basically, we have summation or integration over x of this summation, which is summation over all actions of reward of x and a times pi of theta of a conditional x. So here, this is a probability of choosing action and not density, but doesn't really matter much. But I may switch back and forth between these two formulations, because sometimes maybe it is more intuitive to think about summation, sometimes it's more intuitive to think about integration. I do it mostly in the lecture notes, but sometimes here too. So now we want to compute the gradient of J of rho with respect to theta. So we had this J of rho. We take the derivative of it with respect to theta, and basically I move the derivative inside the integral. It's linear operator, so we can both integration and derivative are linear operators, so I can change the orders. And what I get is R of integral of R of x and a times the derivative of pi of theta with respect to theta times, and then there is integration with respect to rho and integration with respect to a. So I can write it, I reorder it a little bit to make it more explicit. So we have this inner integral, which is essentially saying that we have the gradient of pi theta for a fixed x. We compute the gradient of pi theta multiplied by reward and take average over actions. So, which also can be written. And then this inner integral, we take weighted average of it according to rho, which means that we are essentially computing the expectation of this inner integral when x is coming from distribution rho. So it would be the same, very similar if we have a discrete action space. So integration becomes just summation. So this quantity, gradient of J of rho with respect to parameters of policy, is called policy gradient. So, and this is basically what we want to estimate now. Any questions so far?
So this is basically doing a gradient estimation on the multi-arm bandits, except that the state space here is continuous.
Yes, so this is like multi-arm bandit, you can think of it, or continuous arm bandit essentially, because you might have infinite number of bandits, but then you have excess, so it would become contextual multi-armed or continuous arm bandits, if you want to think about it that way. And this would be the gradient of it. So essentially, if you want to solve bandit problem using policy gradient type of methods. Yes. Any other question? Okay, so if we can compute this policy gradient, then we can update the policy parameter using gradient ascent methods. So basically, as before, we compute this, multiply it by learning rate, and add it to the previous value to get the new parameter space. And gradually it moves, say, if this is policy parameter, and this is the performance, if we start from, so this is J of rho of pi theta. If I start here, it moves gradually up to get stuck here. If I start here, it may go there. So this is local optimization method. So we only, like all the gradients, descent algorithms, we find a local version. Yeah, so I guess there is, probably this would be confusing, but I just want to say in parentheses that there are some recent theoretical work that's showing that sometimes policy gradient methods can find something more than the local optimum. They might actually find the global optimum under certain conditions. But I'm not going to talk about those. So under some condition, they are better than just a local method. Or in a sense, they still converge to local optimum, but their local optimum is actually the performance of the policy at local optimum might be actually very close to the global, the performance of the global optimum. Just make so in order to kind of, there shouldn't be a confusion that it is not necessarily global optimal policy, but global optimum within that policy space. So remember that we are searching in the policy space capital pi of theta, which the optimal policy may not belong to it. So if the optimal policy does not belong to it, these policy gradient methods can for sure not find it. But also, because they're local methods, they may not even find the minimum maximizer within this space. But then this recent result says that, well, under some condition, they may actually find it. But that's, I guess, beyond the point. I guess the intuition is that they find the local optimum within this pi of theta. Hopefully that's not confusing. Okay, so so maybe we can have a few minutes of break. Now is 2, so maybe we can start around 5, 6 past 2. Okay, let's get started. So we have this form for policy gradient. Now the question is that how can we actually compute it? And especially since we are in the RL reinforcement learning setting, so we don't know reward or we don't know this distribution rho. So these are not known. how can we compute it? We do it gradually in a few steps by relaxing some assumptions until we get to a procedure that we can compute it using only data. Okay, so if we knew rho and r, we have all the information necessary for computing the gradient. So this is clear, but just go over it. So for each state x in the state space, we compute the summation or the integral over all a of rxa times gradient of pi theta. So for each of them, we compute this inner integral, kind of. I missed the reward part. And then we weight it according to that term proportional to rho of x, and then take average over all x. So this is in principle, like from information that is available to us, it's possible. In practice, maybe we cannot really do it. Like if the state space is continuous or action space is continuous, this means that we have to compute some integral, which may not be easy to compute. But at least from the information available to us, we can do it. But this is not the RL setting that described. We described because this is not based on the, basically, we don't know R and rho. So now relax it, like we assume that R is known, but rho is not. So we assume R is known, but rho can only be sampled. So we have samples from rho. So we can approximately solve this problem by just sampling from xi's from rho, like n samples, and then computing this summation or this summation essentially. So this summation would be 1 over n of I from 1 to n, number of data points of this as summation over actions of r of xi times a times gradient of pi theta of a and xi. Or if we have integral, this would be by continuous action space, this would be this integral. So this is simple. And since xi is coming from the distribution rho, this would be an unbiased estimate of the policy gradients. So the policy gradient would be, as I had before, an expectation over x of this quantity. So if we compute it, a single sample from it would be an unbiased estimate of our policy gradients. Okay, so this is good. So we can form an unbiased estimate of that quantity, and then maybe instead of doing gradient ascent, we do stochastic gradient ascents because we have a noisy version of that gradient. But if R, because this is still not feasible according to our protocol because R is not known in our interaction. So what we have is essentially agent is initial at state X, which is randomly coming from rho, and then it has to choose its action according to some policy pi theta. So that's the only thing we have. We can do that integration of our actions. So maybe one in parentheses, let's have some interpretation of what that term basically means. So this term that we need to compute can be interpreted as the expectation of this quantity, of course, when action is coming from uniform distribution. So this is essentially like so if I add it by some uniform distribution, which assigns probability 1 over number of actions to this quantity, that would be essentially the same. I multiply it to make it exactly the same. So, but the interpretation of this is that I have an expectation of, so this summation, this expectation of R of x and a, pi of theta of a and x, when a is coming from some uniform distribution. And we have similar thing for the continuous case. So this is basically showing that this integral that we want to, or the summation that we want to calculate, it is as if we have a random variable Rx gradient of pi x, but with actions coming from uniform distribution. The issue here is that the data that we have is not actually coming from a uniform distribution, but is coming from a policy pi theta, which may be different from uniform distribution. So this is basically what I'm saying here. If the actions were coming from a uniform distribution, we could easily form an empirical estimate of these terms. So, but they are not, but they are coming from another distribution, which in general is different distribution than a uniform one, because the parameter of theta and theta is changing, so it is changing. So we are in some sense in some kind of off-policy sampling scenario that what we want to compute is coming from a distribution that is different from the distribution of data that we have. Not all people may call this off-policy sampling, because use of policy when we had this behavior policy and the policy that we wanted to evaluate in that, if we interpret it in that strict sense, then this is not the same issue exactly. But at the high level that what we want to evaluate, which is not value of a policy, but this integral, which is kind of contributing to the policy gradient, we need some distribution, but we have another distribution. So what can we do? One idea is that we estimate R hat from R, and then use that R hat and compute that integral or summation with that R hat. So this would be like a model-based approach. So we learn R hat, which I haven't talked about yet. So we learn that and then use the learn model in order to do calculations. I don't go into detail of it here, but I have a little bit more discussion in the lecture notes. But then the other way to think about it is that we modify this term R of x and a, the gradient of pi theta of a and x, to quantity that can be estimated from data. We basically manipulate a little bit, use some tricks, and then we can estimate it using data. Is this clear so far? Okay, so in this case, so we have this kind of observation that for a function, so let's make it for a function f from R to R, we have it from, say, calculus, that gradient or derivative of log of f with respect to x is derivative of f divided by f. So this is the kind of formula of log of some function. Probably in calculus we have, yeah, like that we have, you had seen it. More generally, for a function that is multivariate, R of p to R, we have the gradient, or with respect to x, of log of f of x is equal to gradient of f of gradient with respect to x of f of x divided by f of x. So this is the formula for gradients. And we are going to use this formula in order to change what we want to estimate. So what we have is that the quantity that we want to estimate was an integral of R of x and a times gradient of pi theta, right? So we use that formula in order to write the gradient of pi theta as, so here, okay, so maybe the result of it, to be a bit more clear, f, it would be f of x times gradient of log of f of x. So basically, I just do this manipulation, and here I use this gradient of pi and substitute that pi times gradient of log of pi to get this form on the right-hand side. So this is a kind of convenient form because now we have policy pi of theta appearing explicitly in the right-hand side. So now we can interpret this as computing the expectation of some quantity. What quantities? These two quantities, when the distribution is pi of theta, which I'm writing it here. So this would be expectation of A coming from pi of theta of R of x and A times gradient of log of pi theta. So this is kind of interesting because now the actions are essentially saying that coming from this distribution pi theta, which is the same distribution that the agent chooses for its action. So now basically, if we have a random variable like this, R of x and A times gradient of log of pi, and actions are coming from that distribution, that would be an unbiased estimate of this expectation, which is equal to this integral that we need. So here, based on this interpretation, we are in the unpolicy sampling scenario, because the quantity that we want to estimate is in the same form, requires the same sampling distribution that our agent is choosing its action from. So that's great. Okay, now, so that was focusing on single x. Now we can focus on x being random, coming from rho, and action being also random, coming from pi theta condition on x. Then this random variable R of x and A, gradient of log pi of A and x, is an unbiased estimate of the policy gradient. So policy gradient can be now written as this expectation, and I can divide this expectation or decompose it to two parts. One is the inner part, which is essentially what I had in the previous page. So it would be R of x and A, gradient of log pi, A of x, when A is random coming from policy pi. And this is condition x saying that we are focusing on one single x. And then x coming from distribution rho. This is kind of like outer integral or outer expectation. So now this basically shows that if you use this quantity and have my samples in this way, then I'm having an unbiased estimate of my gradients. And so I can do stochastic gradient ascent in order to improve my policy. Okay, any questions so far? Is this clear?
I just had a question about the reward. So is kind of like the goal to eventually substitute the reward for like the total reward or
yes.
the return?
Yes. So next I'm going to continuum case that instead of just immediate reward, I will have discounted sum of reward.
Yeah. Okay. Awesome.
So here I think, so basically I start from a simpler problem, and then so that I can introduce these ideas, and then next we just have one more idea maybe. And then that would be policy gradient for more general case. Okay, so I think that's it.
Sorry. When you're doing, like in the homework assignment, when you're doing, a bunch of tuples that are x reward and then x prime, which is sort of, is that considered immediate return? I know you still follow it. You follow it for the whole episode, but for each one, you put it into sort of a replay memory. And
right, but it's
and then you do your updates based on these tuples, which you kind of take as immediate rewards, no?
Not exactly, because the objective is the value function is defined based on like kind of long-term sum of rewards. So value function is still summation of gamma to the power of k of rewards.
Yeah.
Or the data is just like, I guess the data would be in the form of, say, xt, at, x, rt, x prime of t. So that's true. But then, say, if you do, I mean, depends on method or what exactly they do. But say when you compute the Bellman operator or TDR or something like that, you have a component term coming from the reward, and then gamma times the value of the next state. So usually, like say in TD, we have something like gamma v of x prime t, right?
Yeah.
So this is the immediate part, but this is kind of including the long-term effect of it.
Yeah. Okay.
Here I don't do it. Like here, this term does not exist at all.
Mm-hmm.
But like in a few slides, I'm going to add that.
Okay.
Okay, so that's good. But if you use this random variable, we have some sources of bias or variance. So this is unbiased estimate of the gradients if x and a are distributed the way I explained, but it has a variance due to two sources. One is basically, okay, so I define this function g of x and theta, which is essentially expectation of this quantity at particular state x. So expectation is the randomness here is only coming from A. So we are kind of marginalizing the randomness over A. And then we have a function which is a function of x and also theta. So you can interpret this as the contribution to the policy gradient coming from state x. And then if we take integral of this, so essentially the policy gradients that we had would be this g of x and theta, d of rho of x. So this is the gradient for single state x weighted from at different states according to rho. So one is that, okay, so we are trying to estimate this g of x using, say, a single sample here. This introduces some variance. So that's one source of the error. The other source of error is that, or not error, but the variance is that the variance of estimating the policy gradient, which is, so this is basically what I have up there, using a simple sample over state x. So I have only one x coming from rho, and then I'm forming g of x and theta. So this has some variance if I compare it to its expectation. So compared to expectation, there is some variance. So that would be another source of the variance. Okay. Now, one can show that we have, if you want to compute the variance, we can decompose the variance of this policy gradient along the ith dimension. So instead of gradient, I'm just computing the partial derivative with respect to pi theta. So the variance of r of x and a, partial derivative of log of pi theta with respect to theta I, that can be written as the variance of gi of x and theta, and gi means the gradient, the pointwise gradient, the ith component of it. Because remember, or maybe I haven't explicitly mentioned, but this g of x and theta is essentially a p-dimensional vector, because the gradient with respect to p parameters, so we get a vector out of it. if we only look at the ith component of it, that would be g of I. So the variance of the whole estimate depends on the variance of this gradient when the randomness is over the all states. And then the other is the variance of this quantity conditioned on some state x. And then we take average of it with respect to distribution rho. So this is like maybe pointwise variance, and this is the variance over the states. So now what we want to do is to think about procedures to reduce these variances, because higher variance estimate of the gradient leads to worse performance, essentially. So we want to have a better variance or better estimate of the variance of our policy gradients. Okay, so I think I have already defined this. So yes, so okay, so we have, if we knew R, okay, so just going back to the previous setting, if we knew R, and so we could compute the variance, pointwise variance, gradient, policy gradient, we wouldn't have the first source of the variance, but we would still have the second one, which is this term. So just assume that, first we assume that we know we can compute that G exactly, so we're only dealing with the variance of the second source. So the variance of it would be variance of G of I, ith term, when X is coming from rho. So this basically says that if this gradient, policy gradient, the ith term, is not changing over the state space, the policy gradients always say 1 in that dimension, then there wouldn't be any variance over it. But if different states have suggesting different directions for the policy gradient, we would have a variance coming from it. Is this clear? So there are ways to reduce them. So I talk about first randomness of states, and then I talk about randomness of action. So assume that we can compute G of X and theta exactly for any given X. And what I had before or mentioned in the previous slides is that if I only have one sample X1, this estimate, one single sample estimate has some variance or causes some variance in computation of the policy gradient, which is the expectation of that. So remember that we want to compute this. So this would be our policy gradient. When X is coming from distribution rho. So this is a policy gradient. A single sample version of it has some variance. So a way to reduce that variance is that instead of single sample, use more than one single sample. So for example, suppose we have n independent sample x1 to xn, all coming from distribution rho, then we can estimate the policy gradient by 1 over n summation of g of xi from 1 to n. And then this essentially, the variance of this estimator along dimension I would be 1 over n of the variance of just a single sample one. So if n goes to infinity, then this variance goes to 0. So this is good. Basically means that if I want to compute the policy gradient, if I increase the number of initial points that I have, I would have a more accurate estimate of the policy gradient with a variance that goes down with the rate of 1 over n. If I could compute G exactly, which is not the case for us, but at least in this, for now, we assume we have it. So I guess some parts of this slide is gone, but that's not, I mentioned it. So what is the issue here? So do you see any issue if with this suggestion of letting n going to infinity? Or choose it a large number?
Takes too much time?
Takes too much time. Okay, that's good. Now suppose that you have a budget of, say, capital N interaction with the environment. So you have a capital N interaction with the environment, like episodes, for example, or maybe I use T, for example. So what happens now? If I use n of them to estimate the policy gradient of current policy, it means that the number of gradient updates that I may have would be reduced. So basically, the procedure would be like this. So I start from theta 1, for example, and then use 1 to n in order to estimate the policy gradient of it like this with policy 1. Now I do an update. So some alpha of that gradient of theta 1. So that's my pi 2. Now I need to evaluate pi of theta 2, which basically means that I use, for theta 2, I use n plus 1 to 2n. And if I do this procedure, I can do at most t to the divided by n number of policy gradient updates. So if t is limited, like it's not infinity, it means that there is this kind of trade-off between how accurate I want my policy gradient to be versus how many gradient updates I may have. On one hand, if the policy gradient is very inaccurate, has a lot of variance, then each step of gradient improvement, policy gradient improvement, would not be in the right direction. In expectation it is, but in that particular sample may not be. But then on the other hand, if n is increasing, then I have a very accurate estimate, but I can only have one update essentially. So there is this trade-off. That's good to know. And I'm not sure, probably there are some results, but I'm not sure whether we know what is the optimal trade-off in, if we have t, how should we divide these things for policy gradient methods? I think there are some results for stochastic gradient descent in the context of, say, supervised learning, but RL might be a bit different. Okay, so that's one idea. Any question?
How about variance due to the variance of the reward function?
That's a good point, actually. Yeah, that's a good point. And we could have that. Like here, I wrote small r, but I could write it r of x and a, and nothing would be different except that I needed to take integration over the distribution of reward. And then I think the only change would be like here, essentially, in this, when I focus on single state x, how much the variance of reward adds to the variance of this estimate.
Right, yeah. I was wondering if people do these kinds of tricks. I think I've seen it at a couple of places where you subtract the baseline reward and things like that.
Yes, that's
the reason.
That's a very good point. And so here I only focused on just assume that G, like for single state X, there's no variance. The only variance is coming from the variation of where I'm choosing an X space, state space. But what you're saying is exactly correct, is that there is also variation in single states, either due to reward or also due to choice of action of the policy. Because remember, policy is stochastic, so if I only have one sample, I'm only forming kind of a single sample estimate of some expectation. And that's going to be the next thing I'm going to talk about.
Awesome, thanks.
So here, as you mentioned, basically, we want to consider the variance of estimating g of x and theta by using a single sample r of x and a, gradient of log of pi of theta of a and x, with a coming from this policy. So here the randomness is over choice of actions. Okay, so this is the idea, and this term also could be variance of, could be a random reward instead of, so here what I'm showing is that the randomness is over only because of the policy, but reward is kind of deterministic, but not much would change if we change it to capital R. So we have this kind of identity that is, I mean, it's not difficult, we are going through it, but may not be trivial or may not be intuitive if you haven't seen it before. So suppose what I do is that I have this expectation of gradients or log of partial derivative of log of pi theta with respect to theta I. So I focus on ith dimension of that gradient, and then I add some function, some b of x here. So b of x, you can think of it when x is given, it's like a constant value, like 5, 10. But in general, b of x is a function. It's a function from states to r. But when I'm focusing on one point of it, 1x, then this acts like a constant. And I want to compute this term. And it becomes clear why I will do it. So just write it. Let's write it. So it would be, probability of choosing action is according to pi of theta of a and x. We have this log term, log gradient of, or derivative of log term, and then we have b of x term, and then your integration is over action. So what happens is that, okay, so I kind of revert back to the previous formulation that I have. So I take pi and log pi, gradient of log pi, and write it as the derivative of pi theta with respect to theta I. And then I have b of x. Now notice that b of x is not a function of action, so I can take it out of the integral, right? So I'm taking out here. So I will have integral of gradients or partial derivative of pi theta with respect to pi I. Is this clear so far? Okay, so what I do now is that I take the partial derivative outside the integral because it's a linear operator. Both of them are linear operator. I can change the order of it. So I will have b of x partial derivative of the integral, which is pi theta, a conditional x, over integration over actions. This value is equal to 1, right? Because it is a stochastic policy, so it's defining a distribution over actions. The sum over a probability distribution over the whole domain, action space here would be 1 if it's a valid probability distribution. So this would be 1. Now I'm taking derivative of 1 with respect to some parameter. But 1 is not a function of parameter, it's constant. So it should be 0. So this becomes b of x times 0, which is 0. So this is interesting because it shows that if I add this, or I have this term of derivative of log times b of x for each x, the value of that would be 0. So I'm going to use it. By doing this, basically, the policy gradient that I had, the contribution of single state of it, is this expectation. So we have expectation, and expectation here is coming from pi theta. Derivative of log of pi with respect to theta I times r is equal to the same thing plus b of x. If I add b of x, nothing changes. So that's great. So I can't add a function to my policy gradient and nothing would change in expectation. So adding state-dependent function b to r, x, and a does not change the expectation, but it may change the variance. The variance of the new random variable, which would be like, if I consider this thing. So this is a new random variable. The variance of it I can change by choice of b. And so this derivation was for a single, with respect to ith dimension of this policy gradient, I can choose different b's for each dimension. So for each dimension I, we can use a different state-dependent function. So in general, we can have a function b, which takes from domain with domain state and to the range of RP. So, and then the policy gradient, which is this term, and we had it before, would stay the same if I add this b of x here. So here I'm kind of using some notation to make it kind of compatible with vector notation. So this is this belongs to RP. This is R, which is scalar. So this one is a vector of p different one or p1s. So this capital 1 is 1, 1, 1, p of them. And then I have this kind of component-wise or entry-wise product, which is also called Hadamard product, of this reward term or modified reward term plus gradients of log of pi. And these two things are essentially will be the same. So the expectation of the same. Usually, I think people in practice just use a baseline, a constant baseline. So it's they wouldn't choose p-dimensional baseline, but they just write it in this way. So for all dimension, they consider the same baseline, but this is not the most general case, and it wouldn't be necessarily leads to the best, the minimum variance estimator. So this function, okay, I haven't said that, but this function b of x or b of x up here, it's called the baseline. And if we choose it, we may be able to reduce the variance of our estimator. Okay, so here the baseline can be used in order to minimize the variation of p-dimensional random vector. So we have a random vector, it has some variations in each of its dimensions. How should we measure that variation? One way to measure it is using variance. But of course, variance is defined for a scalar random variable. So we need to somehow use a quantity that can deal with p-dimensional random variable. And we can do it easily by just saying that we take the variance of each of the dimensions and just add all of them. So that's one way to do it. So now the goal becomes finding a function b from x to rp such that for all x's, this is minimized. So what is minimized? The summation of a p-dimension of variance of rxa plus bi of x of partial derivative of log pi with respect to theta I, and here it's condition of x. So I want it to be minimized. This can also be written as we take the covariance matrix of this random variable and then compute the trace of it. So that wouldn't be different. So for random multivariate random variables, we have covariance instead of variance. So we can write this objective in the form of covariance matrix too. But trace would be essentially a summation of the diagonal terms. So we don't need all the terms. We just need that term. And there is some calculation. It's not very difficult, but you can see that if you solve this optimization problem, basically compute this thing, expand it, and take derivative with respect to bi of x, and make it equal to 0, you get a solution like this, that bi of x would be minus of expectation of r of x and a, so this is random, of partial derivative of log of pi of theta a of x with respect to theta I, the whole thing squared. Then this divided by expectation of gradient of log of pi squared. So that's what we have in the form of, if we only want to choose a single scalar function b, instead of having separate one for each dimension, the form would be essentially very similar. So we have norm of gradient of log of pi. Yeah, I think even, I mean, here I guess we can have a norm form too, so it doesn't matter much. No, that's not true. Okay, so here this is true. Okay, is there any questions so far?
I kind of have more of like, I guess, the higher level question on, I guess, the derivation and the selection of B. Is there kind of like an intuitive explanation, or is it mostly just like solving the minimization problem?
This is specific form you mean, or in general the choice of baseline?
I guess in general, but it could also be like this form if it helps like explain it.
Right. No, I guess I don't have a very kind of compact explanation, but basically it is saying that by adding baseline, I have a random variable. If I change the shift that random variable somehow, by adding some baseline to it, the idea here is that if I choose that baseline in some nice way, that would reduce the variance. Okay, so maybe a better example would be.
Yeah, I guess it kind of makes sense because the baseline's a function.
Yes.
Based on the algebra, or like the manipulation that you did, it shows that like the baseline actually doesn't affect the expectation.
That's right.
But it reduces the variance.
It can change the variance, yes. So essentially something that doesn't change the expectation, but can change the variance. And here kind of, yeah, the idea is that if you shift random variables in a certain way, you can do it somehow that reduces the variance. But I guess what I'm saying is not very, just kind of repeating what it is doing, not what would be the intuition of it.
Yeah, okay, so the reason we want to do this is because the expectation remains the same, so it's still an unbiased estimator for the gradient.
Yeah.
And the variance is reduced, so our confidence in the approximations that we generate is higher.
Yes, that's right. Yes,
okay.
That's the intuition.
So I guess one intuitive explanation may be, for example, if we have the form A minus B and A has some variance in it, and B has some maybe similar amount of variance in it, and then we just cancel the variance by minus the two terms, by taking the difference of the two terms. So exactly cancels the second term, exactly cancel the variance of the first term, something like that.
I guess that's control variance interpretation.
Oh, yeah.
Yeah, so yeah, I guess that would be, I mean, we can introduce control variance is that if you have two random variables that are, yeah, I guess if you have two random variables that are correlated with each other, you can, Yeah, well, okay, so maybe let's see if I can.
Yeah, I guess it would depend on like the covariance, right?
Yes, so.
But yeah, if they're correlated, then the covariance, or like it's like +2 AB or whatever that formula is, right? So then that would be negative. So that would reduce the overall variance.
Yeah, so I guess the idea is control variance is that you have a random variable x, you want to estimate its expectation, and you want to have a minimum variance estimate of it. And then suppose you have another random variable y, which you know its expectation y. Somehow you know the exact value of expectation. The control variance idea is that if I form a new random variable that's called z, of x minus or x plus 1 minus expectation of y. So here the idea is that, maybe I just write it. So this term doesn't change anything doesn't affect the expectation, because in expectation, these two cancel each other. But if x and y are properly correlated with each other, we kind of reduce the randomness of x by having some random variable that is correlated with it. So again, I guess this has to be proven that this is the case, and it may provide a little bit better interpretation, but I guess it depends on whether you find this more intuitive or not. Baseline is acting essentially like this y. When expectation of baseline, you know it is 0. So adding it doesn't change anything, but if baseline is correlated properly with this random variable x, which is your sample from policy gradient, then this may reduce your covariance. In practice, I think people don't really use, well, I don't know, but I guess it's not very common to use this specific form of that, but people use simpler heuristics. So for example, they just use value function as the baseline. Yeah, I haven't got to this, but you will, okay, so in that case, I guess the baseline would be something like,
So the advantage calculation.
Advantage calculation, exactly. So here we don't have value function. R is essentially like Q function because it's state and X. So people may use just this instead of baseline, which is like the average value that we get at that state if we follow policy thing. And that, okay, I'm not 100% sure that it's guaranteed to reduce the variance. Probably it does, but I'm kind of sure that it wouldn't be the optimal solution. But that's easier to compute than this baseline that I have here. Okay. So I think I have to go a bit over time, probably 10, 15 minutes maybe. Feel free to leave, but this is going to be the end of this lecture. And then I talk about next lecture or what happens to that, because we are out of weeks. Okay, so now let's talk about policy gradient for continuing tasks. So we derive the policy gradient for immediate reward case, but here we want to have the case that the agent interacts with the environment for more than one time steps. So what happens here is that, okay, the performance depends on the dynamics P of pi theta 2. And as we change theta, then the dynamics P of pi theta also changes. And as a result, the distribution of states in the future also changes. So the reward that we get in the future also changes. So this addition of dynamics may seem to complicate the computation of gradients compared to the case of immediate reward. But it turns out that we can write still policy gradient in a very nice, kind of an elegant form, with relatively easy to compute. I mean, relatively easy, I guess it has some footnotes, because it requires computation of some quantities which are not necessarily super easy, but we do it in RL. Like, we need to compute the value function. Value function is not easy to compute, but we know how to do it. So this becomes clear as I go in a few slides. Okay, so I need to introduce some notations. So recall that okay, I think we had seen this before. P of pi to the power of k, which was basically the probability of probability distribution of following, starting from state x, following policy pi for k steps. And so we are at time, say 1, we go multiple steps, and there's a distribution where we end up. So this is the distribution p pi of x and k, or so this is like starting from x, and then we go k steps forward. So I think the notation that I used before was p pi to the power of k, but here I'm using this notation that I use k as a part of this kind of the argument of this notation, of this p. And this notation also makes sense, because if we have a finite state problem, and if we write p of pi in a matrix form, which we had it in a few lectures ago in the value function approximation lecture, the distribution of being at some state after k step would be exactly the same as taking the kth power of that matrix. So in matrix forms, actually would be the usual power matrix exponentiation notation computation. Okay, so we need another definition. So this is called discounted future state distribution. So this is the distribution of future states, but discounted. Okay, so what does it mean? So I have a summation over k and compute the distribution of starting from x, going k step forward for all the values of k from 0 to infinity, but give a weight of gamma to the power of k to it. And then, so multiply it by 1 minus gamma. So ignore 1 minus gamma. The intuition here is that we go to, in the future steps, k steps, but the weight of going there would be just kind of decaying according to gamma to the power of k. So that's the kind of the future state distribution. The reason we have 1 minus gamma is just to make sure this would be a valid probability distribution. So which means that, so for example, the probability starting from x, any x, the probability of going to state space, being in a state space, is 1. So this is what we require from a valid probability distribution. And it's, of course, it has also other basic properties. But so this is the idea, and we use this by notation of rho gamma of x and p of pi. This might be a bit cumbersome, and we don't need it in this lecture actually. So we may just use it rho pi gamma of x. So this is the kind of the notation that we want to use. And why is this relevant? Is, well, one way to think about it is that it's closely connected to the value function. So I can write the value function in this form. So how's that? So value function v of x for following policy pi, we had seen it a long time ago, that it's the expectation of summation of gamma to the power of t of rt when initial state is x0. So this can be written as summation over t of gamma to the power of t of expectation of RT conditional on x0 being at x. So this is essentially saying that in expectation, how much reward I would get if t steps ago I was at state x. And I can write this, just expand the expectation. So expectation would become integral of r of x prime when I start from x, go t step ahead to x prime. So p pi of d of x prime condition x and t, and then weighted according to reward. So that would be the expectation. And then I move the summation inside. So I basically move the summation and gamma to the power of t inside. So I would get rho of pi of gamma of d of x prime, conditional x of r of x prime, which would be, if I write in form of expectation, it means that value function at state x is the expectation of rewards when that random variable x prime is coming from this discounted future state distribution. And then for normalization, I have to have 1 divided by 1 minus gamma 2. So this is nothing strange. It's essentially saying that value function is like average reward, but when the distribution x is coming from this discounted future state distribution. So here, what I had is that discounted future state distribution when I started from a single state x, but I can also define the case that my initial distribution is according to rho, and then I take average of the distributions that I would get. And this would be shown by rho of pi and gamma. So this is essentially saying that we start from state x, we start from some initial states distributed according to rho, and then we follow it, and then we weight it according to gamma to the power of k. That would be the distribution that we have here. So one thing that is kind of, it's obvious, is that the performance measure, so performance measure, maybe I have it rho here. The performance measure that is, if you recall, it was exactly like this. It was expectation of the value function when x is coming from distribution rho. This would be exactly the same as expectation of reward when x is coming from discounted future state distribution. And then there is normalization factor. Okay, so this is kind of interesting, and it's kind of compact notation. So there is one interpretation for this quantity rho of gamma of x. So this is the interpretation. So the interpretation is like this, that the agent starts from state x, and at each time step, it decides to whether following policy pi or not. It follows policy pi with a probability of gamma, or terminates the episode with probability 1 minus gamma. So say gamma is 0.99 with probability of 99%, it follows the policy, and then, or with probability 1%, it kind of terminates the episode. And then at the next time, it does the same process again and again. So we can have this kind of interpretation for what this distribution is actually encoding. This kind of modified encoding of how agent interacts. So this makes a problem more like, not more like, it makes it an episodic problem. So continuing problem becomes, discounted continuing problem can be interpreted as a episodic problem where the protocol of the agent's interaction with the environment has this chance of termination with probability of 1 minus gamma at each time step. Okay, so that's kind of as a side note. That's not important. Any questions so far?
So this discounted future state distribution is non-stationary throughout training, right? Because of the policy changing.
Yes.
So then if we try to use a baseline like earlier, then we would have to recompute the baseline after each update, right?
Yes. Yes.
Okay.
So in general, I guess in general, baseline is a function of policy, optimal baseline at least. And then, so usually the methods update the baseline in some way as they update the policy.
Right, makes sense, thanks.
Okay, so this is policy gradient theorem, which is kind of the summary of many things that we have talked about for the case of continuum case. And it's kind of very, I think, nice results because in a very compact and elegant form, it shows what is the policy gradient of basically what is the policy gradient. So the form, so what I have here is like the result of Reed Sutton and others from 2000s, except that I guess I think the last term, so I'm writing in 3 different forms. The last term, I guess, is not mentioned in that paper, but it's kind of known. Even I guess at that time it was known. So let's go through it. So basically, policy gradients of pi theta is, okay, this quantity, which looks a bit scary, but basically saying that, okay, k from 0 to infinity, we have a weight of gamma to the power of k of this integral. So what is this integral? This integral basically saying that we start from distribution x from distribution rho. So we choose x from distribution rho, and then we follow pi theta for k steps, and we get to the state x prime. So I start from x, go k steps ahead, I get to x prime. And now I compute this integral at that state x prime. And what is that integral? It is essentially the contribution of that state x to the policy gradient. And if you recall, this is very similar to what we had before. If in the immediate reward case, if you substitute it with r of x prime and a prime. So if you have, so here, okay, let me go through it. So this integral is integral over a primes, over actions, of gradients of pi theta of a prime condition x prime, so this is gradient of policy, times the value function or action value function at that x prime and that a prime. So I take average over actions, and then that would be the contribution to policy gradient coming from that state x prime. Now I take average over all x primes here, and then, so this was for step k. I change k's and give different weights of gamma to the power of k to it.
In second line, there should be a log, right? There is a log missing.
Yes, so I think what I wanted to write, that's a good point. Thank you. So this one, what I wanted to write was probably this form without that. So I just wanted to go, okay, so let's go to the next line. So next line is essentially just, so for next line, I just take all these terms and substitute it with discounted future state. So that becomes rho of pi theta of gamma of d of x times this integral, the same integral as before. And this term, you should ignore that term. And then, so this is essentially a bit more compact form of it. And even more compact is that, well, not more compact, it's kind of different form, is that we use the same trick that we convert gradient of pi to gradient of log pi, but change the distribution over actions. So here I convert this summation to this some expectation, part of this expectation. So this expectation is over both states and actions. The part that is, this integral would be the expectation over actions of what? Of 1 over 1 minus gamma of expectation of when x is coming from future, discounted future states distribution, and a is coming from pi theta of gradients of log pi times q of pi theta of x and a. So that's a kind of compact form. All the information about dynamics goes inside these quantities, like the future state distribution. And to compute the policy gradient, I only need to be able to compute this form and generate samples from x and generate samples from a. So if I can generate samples from this future state distribution, discounted future state distribution, generate samples from a, and then compute this quantity, then everything is fine. If I have one sample of it, it would be like one unbiased sample from policy gradients. Maybe just one thing is that, okay, see here, I guess as I mentioned here, in the immediate reward case, we had instead of q of pi theta, we have reward. So essentially, instead of, well, having q, we are considering the influence of future rewards in our computation. Okay, so is this good? Okay, so this is, let's try to prove it. I think this is kind of interesting because you had seen very similar argument before, but there are also some nice kind of ideas here. So we write the value function at state x as the expected value of the action value function. So v of pi theta at state x is essentially q of pi theta of x and a when I'm taking average of policies, average over actions according to policy pi theta. So this is kind of what we had seen before. This is a definition of v and q. So now I take the derivative of v with respect to pi theta at state x. So here I start from state x, and then at the end I just take average over all states according to distribution rule. So if I know this, then everything would be fine. So I just take gradient of like here, add it here, so gradient moves inside. So I have a gradient of these two terms. I use product rule for derivatives to get that we have gradient of pi theta times q plus pi theta times gradient of q. So this is kind of interesting. So now I have, okay, so this term is kind of clear. This term is also clear. Now I need to compute the gradients of action value function with respect to policy parameters. So that's our next step. Now I use the definition of, I use the Bellman equation to expand the action value function to what? So q pi theta of x and a is reward of x and a plus gamma p of d of x prime, x and a, v of pi theta of x prime. So which of these terms depend on theta? Well, reward doesn't, p doesn't, because I guess this is kind of the trick. By choosing action A here, at the first step, I get rid of dependence on the policy and postpone it to the next step. So the dependence of policy only appears in this last term, v of pi theta of x prime. So if I take derivative, many of these terms cancels or simplifies. So derivative of q pi of x and a would be gamma times p of the x prime conditional x and a times gradient of v of pi x prime. Okay, that's great. Now in previous page, I already calculated this gradient of v of pi at state x. So I just need to substitute the same thing, but for x prime. So if I do it, I get something like this, that gradient at state x is gradient of pi times action value function plus gamma times gradient of v at state x prime when x prime is coming from p of pi theta, starting from x. Okay, I think that's, okay, yes, that's fine. So this is kind of interesting because this is like a Bellman equation, but for gradients. Just consider this is a gradient essentially. Left-hand side gradient, right-hand side gradient. And this is like a reward, but let's call it, which is a function of theta and q. So we have this kind of Bellman equation again for policy gradient at each point x. So this is interesting. I mean, the policy gradient, we don't use this Bellman equation much, we just expand it. And I'm not sure if people use this as a Bellman equation much or not. I haven't seen. Maybe they do, but I just missed it. But we have this Bellman equation for policy gradient, state-wise policy gradient. Okay, so now we have x prime here. Let's expand it again. Let me see if I, so okay, so we expand it. So policy gradient at x would be the first term plus gamma times p of x prime. Expand it, it would be gradient of pi at a prime x prime times q plus another gamma times p of x double prime, conditional x prime, of gradient at x double prime. So if I follow this pattern, expand it kind of recursively, we get to this equation that gradient of pi at state x would be gamma to the power of k, summation over k of gamma to the power of k, of going k step forward at x prime of this quantity, which is essentially of this form. Like this form, and I guess what is the other one? The other one is coming from here, and so on and so forth. Yeah, I guess that's good. So basically we expand it, and then we can also use the notation of future discounted future state distribution and replace all these summations here and k steps to just write it as rho of pi theta gamma d of x prime and x of this integral of gradient of pi times q of pi at x prime. And so that's kind of proves the first two statements of the theorem. The last statement is just a substitution that we had before, that we can substitute pi, gradient of pi, with pi and log pi. And if we do the same, we get this inner integral becomes, we have a pi, and then we have these two terms. So now, because of this pi, I can interpret it as expectation when samples are coming from distribution pi, which is nice because then if I have only sample from that distribution, I can form an unbiased estimate of this inner expectation, inner integral. And then I have to what it remains to be done is to have samples from this rho of pi theta of gamma. Okay, so I guess the last step is easy. The performance was defined as v pi of x when x is coming from distribution rho. What we showed in previous slides was just for single state x. So now we only need to take average over all x's. So if we do that, everything would be the same, except that here we have rho of pi of gamma. There's no condition in x, so that's a kind of without x version of it. And that would be the same. And from here to here, we do the same trick of changing log pi, changing gradient of pi to log pi and getting some pi out of it. And this is kind of the desired result. So this last, okay, so the results, I think, if I remember correctly, this last statement wasn't the original paper. This, actually, I guess this is statement, which is equal to this statement. It was, but I mean, this is a trivial thing. By that time, people know how to modify, take that, gets that log pi term, or gradient of log pi. Okay, any questions so far? Okay, so let's try some final comments on this. So this theorem, it's kind of, I see it as an elegant formula for policy gradient. It relates a policy gradient to discounted future state distribution, the action value function, and the gradient of pi. And if you want to compute it in an RL setting, we can do it. We have to estimate it using samples. So how can we do it? We can have, okay, so what we require essentially is that we require x coming from distribution discounted future state distribution, action coming from policy, and we need to know action value function there. And then if we do these things, this random variable here, gradient of log pi times q of x and a, that would be an unbiased estimate of policy gradient. And then we can use it in a stochastic gradients ascent formulation in order to improve the policy. And then all the, I guess, all the things that I mentioned about reducing the variance also is valid here. So if I have more samples from X, I have a more accurate estimate of basically this policy gradient. I can add a baseline to this R, to this Q, in order to reduce the variance. So I can add or subtract B of X, and then I can find a variance. I can find a B that is minimizing the variance of it. In practice, people just use, say, the value function there. So for the subtract value function. So they have B of pi theta of X. So we have this quantity, which I think I'm not sure I mentioned in slides or lectures or not, but this is called advantage function. So advantage function is something like action value function, with the difference that saying that how better that action is compared to the average value of that state. If advantage function is positive, it means that that action is better than average value of that average value of that policy or policy choosing actions there. So it's better than value function. If it is worse, means that that action is worse. Or if it's negative, it means that the action is worse. So this is one way to do it, but there are other ways. Okay, so I have some comments about each of these three. I guess the second one is actually easy. But first is that how can we sample from rho of x, rho of pi theta of gamma? So it's relatively straightforward in the on-policy sampling scenario. So agent starts an episode from x0 coming from rho, and then follows pi theta. And then what happens is that it gets a sequence of x0, x1, x2, and so on. So each of these are coming from, basically they're following policy pi theta for k steps. So their distribution is d of rho of x times p of pi theta condition of x and k. So this is their distribution. So this distribution of following policy pi starting from x, starting from initial state rho, or distributed according to rho, following policy pi for k steps. But then if you compare this formula with the definition of future state discounted future state distribution, we had a gamma to the power of k there, which we do not have here. So its effect is basically is that if we are at the state k step ahead, we need to multiply gamma, the weight of that gradient that we compute at that state, with gamma to the power of k. So we get this term, like this is the inner integral. Now we can suppose we can compute it now. The effect of it should be multiplied by gamma to the power of k in order to be able to have a kind of unbiased estimate from this distribution, discounted future state distribution. In practice, people, well, I don't know in practice, maybe it's changing, but this wasn't known for a long time. So what people have been using was just generating these x's and then computing something like this term or an unbiased estimate of it and just add all of them together as a policy gradient or as an estimate of policy gradient. The result would be a biased estimate because the distribution wouldn't be discounted future state distribution, but undiscounted future state distribution. So how much in practice it affects the results, I'm not sure. But if you want to do the policy gradients accurately, in a sense that we get an unbiased sample from it or estimate from it, we have to have this way to this gamma to the power of k there. And this is kind of surprising because I think this was proved, or this was brought up that people had been doing something wrong only, I think, recently, like 2000, maybe 13 or 14, I think. So this is kind of interesting recent results, relatively. Okay, another way from sampling from this is that direct sampling from rho of pi theta of gamma is to follow policy pi, but at each step terminate the episode with probability 1 minus gamma. So instead of going up to infinity, we make it an episodic problem, but we terminate it with some certain probability. And this comes from the interpretation that I had a few slides ago. Just this. Oh, okay. Okay, so this is coming from this interpretation that we are agent following policy X, but at each step, there's a chance of termination. So if we interpret it that way, that gives us a way to terminate it. We can either do this or explicitly add that gamma to the power of k. Okay, the other comment is sampling from policy pi theta. This is not an issue if we are in the unpolicy case that the agent is actually following policy pi theta, because the sample A that is generated is actually coming from the same policy. So this is easy. The other issue, which is computation of Q of pi theta of X and A. So this is the important one. So how should we compute this? So this is this is interesting because it basically says that to compute if you recall, we started the policy gradients or policy search methods with saying that we only represent policy explicitly. And we just ignore the action value functions. But after doing all this calculation, we see that in order to compute the, say, policy, the gradient of a performance with respect to policy, value function appears somehow. Now we have some choices, but we need to estimate it somehow. We either can use a kind of explicit, say, architecture or estimator for estimating this value function, or use something like a Monte Carlo estimate for estimating it. Maybe before that, the basic problem is essentially, in order to compute this, we need to solve a policy evaluation problem. We need to evaluate the performance of this pi theta at state x and a. And we may use different action value function estimators that we have developed so far. Okay, so this is a simple approach which doesn't require explicit representation of a, say, value function using, say, neural network or a function approximator, just building or estimating it implicitly. So a simple approach is based on Monte Carlo estimate of q pi theta of x and a. This is, if we do this, okay, so how does it work? Let's first see how it works. We are on policy setting, and agent is following policy pi theta. It generates x0, a0, r0, and so on and so forth when actions are coming from that policy. So if we have this sequence, we can define a return. So the return at time t is essentially the reward that we get, discounted reward that we get from time t up to infinity. And the good thing about return is that it would be an unbiased estimate of the value function at xt and at. So essentially, you can think of it like this. Okay, so say these are different times at t equal to, say, 0, 1, 1, 2, and then this is time t. So the value function here at this xtat, so this is continued. So we can use a Monte Carlo estimate, add the rewards from this point up to the infinity, and that will be an unbiased estimate for what I want here. And I can do this thing for all of these states that I have encountered. Like I can do it for time t, I can do it for time t minus 1, I can do it for time 2. So having a trajectory, just one rollout, I can estimate all those returns, and that would give me an estimate for q at those states. Okay, so yeah, basically we replace the action value function with the return. The issue with this approach is called reinforce algorithm. This algorithm, if you do these things, is called reinforce algorithm. It was derived in a different way. So it was 1992. It wasn't derived using policy gradient theorem, but they just directly went for something else and then showed that the computation leads to certain procedure, which is exactly what I described here. And kind of the funny thing is that the name is reinforce, and people often confuse reinforce and reinforcement learning. They're two different things. Reinforce is one algorithm to solve reinforcement learning problem, and it stands for something strange, or at least not intuitive, not strange. So it's called reward increment, non-negative factor, offset reinforcement, and characteristic eligibility. And then they, Williams put all of them together, made a reinforce out of it, but doesn't have any clear connection to reinforcement learning. But this is actually, if you see, it's kind of the update rule has all these elements. Okay, so this is great. So the issue with this approach is that reinforced return is a high variance estimate of the action value function. So what can we do about that? One thing we can do is essentially use some kind of baseline in order to reduce the variance of a Monte Carlo estimate. And that's, I guess, one of the main reasons we use baseline. But then another approach is use a more general action value function estimator that might have lower variance compared to a Monte Carlo estimate. The Monte Carlo estimate is great because it's simple, but it's not necessarily the best, most sample efficient way and has smallest error. So what can we do? We can do any method that you have learned, like different TD methods, LSTD method. We can use fitted value iteration or fitted Q iteration, but for policy evaluation. So the way I presented it was for control, and we want to find the Q star, but we can use the fitted value iteration with fixed policy pi theta. And then gradually we update it as we change the policy. If we do these things, so all these methods require an explicit representation of the value function, right? All of them we use, if it's a large state space, we use some function approximator. If it is small state space, like a discrete set, use a lookup table to represent the value function. So all of them require an explicit representation of value function in addition to explicit representation of policy, which is required for the policy gradient. These types of methods are called actor-critic. And basically actor refers to the policy because it is acting in the environment. And critic is essentially refers to this value function estimator, which evaluates or criticizes how well this value function, how well this current policy is. So this is called actor-critic method. I think there are, I guess, two usual things. I mean, I don't know if there is any standard or not, but so actor, usually it's referred to policy gradient type of methods, actor-critic methods. So the actor is always usually improved using some form of policy gradient or variation of it. But I think it can be more general. So I guess it can be interpreted as methods that do other ways of improving policy, some form of maybe policy improvement, which are not necessarily policy gradients. So that's, I guess, debatable. The other thing is that critic usually refers to a value function estimator that are somehow explicit. One can argue that Monte Carlo estimate that we have here is also estimating the value function in a non-parametric way. So it's using data, it is computing the value function at those states, but doesn't have explicit representation. Whether it is actor-critic or not, usually people don't consider it as actor-critic, but based on that interpretation, you can consider one special form of actor-critic. I guess Sutton and Barto's book doesn't consider it as actor-critic. And that might be okay, because then otherwise all methods become actor-critic. Okay, so there is an issue in actor-critic methods. One is that if you use a critic like a TD-based method, it induces some bias, because the estimate that we get from critic may be different from, maybe its expectation may be different from Q pi theta. So especially this is the case if you use a temporal difference type of methods, because they use a bootstrapping. So they use the current estimate of value function, which might be wrong. So there's no guarantee that they provide an unbiased estimate, and often they provide a biased estimate. So it means that some of the nice things that we had before, or the theory that we had before that was assuming that everything is unbiased estimate of that policy gradient, we don't have it. So if we do stochastic gradient ascent, we are moving in a direction that is a bit off. How much that bias is important and how much that variance is important, like we reduce variance but may add some bias, I guess that's not completely well known. Usually, I guess in practice, actor-critic methods, even though they add some bias, they perform much better than, say, using just reinforce, which is unbiased but high variance. Okay, and I guess the other, I mentioned the explicit representation of both policy and value function. The other thing is that actor-critic methods bring together some of the benefits of both value-based and policy search methods. Because, say, for example, now we can work with continuous action spaces easily if our policy can represent them. But, and but benefit from like ability of policy evaluation methods that are sample efficient. Okay, so as a just summary, so policy search methods are about explicit representation of the policy and searching within the policy space. But we had seen, we just saw that like method, like a policy gradient method, something like value function comes to the picture at the end of the day. Value function is an important object in RL. The other thing is that the search might be guided by the zero order or first order methods. Today I talked about first order methods. In the previous lecture, I talked mostly about zero order ones. So there are more advanced method policy gradient methods. Many of them are based on this idea that policy gradient is essentially saying the direction of local improvement of the policy. But how much should we make how large our step size should be? Should we take a big step or a small step? So there are some methods that are based on this idea that because this is local information, we should be careful about how much we move and put some kind of constraints on the amount of the move that we have. And if we do these things, we get some method like trust region policy optimization, TRPO, as one of the examples that put some constraint. The other kind of interesting results is we should try maybe to benefit from the geometry of the policy space in order to think about how we are updating it. If you're familiar with supervised learning, this is somehow like in say Newton-based type of optimization, second order method. Newton method looks at the local geometry of the function in order to decide what direction it should go. So we can do something like second order methods that looks at the geometry of the performance in the policy space and do something like second order method, but not exactly with Hessian, but something called natural gradients.
Okay, I found this on the web for natural gradients. Check it out.
Okay. So you can search for it, or I think I have given some of your readings are this natural gradient. So, so I guess we have TRPO, I guess PPO, and more recently is I guess mirror descent policy optimization. There are other methods like natural gradient, I guess, natural policy gradient, which looks at second order information. And actually, one can see that many of these things are closely related, like natural policy gradient and TRPO are very similar. Okay, so I guess that's all. I didn't go into these, but there are papers that you can read, but the basic idea is essentially, we have policy gradient, now let's follow it. Okay, and these are just references. Okay, is there any question?